Next is the rearrangement in SN1 reactions. Because in SN1 reaction, carbocation is formed and when the carbocation is formed, rearrangement is possible. For example, if we start with this reaction, say this, and we added to it C2H5 or OH, boiled. What will be the product formed? So here the nucleophile is C2H5O negative. This is a nucleophile. And if we see the mechanism, if it follows SN1 mechanism, the first step is that this Br will go out. You will get this carbocation. This is your 1 degree carbocation. Now it will rearrange. This methyl shift on this carbon. This is called a methyl shift. To produce more stable carbocation. So this is your 3 degree carbocation. It's more stable. That's why this process is feasible. Next is this ethoxide ion, OC2H5, attack here to produce the final product. So this is your final product. Okay, but here you can you see that in case of 3 degree carbocation, when 3 degree carbocation is formed, so it can get with different ways, 2 different ways. Like one is that your nucleophile attack. So this is your SN substitution reaction. One way is to obstruct the proton. Okay, there is a suppose hydrogen abstraction from alpha carbon. Remove hydrogen from here. Here is a hydrogen. So when this hydrogen is removed, you get positive charge here. So the product formed is now this. This reaction is elimination. You can write it E1. This will be your SN1. So this is elimination reaction. As Br is removed here, hydrogen is removed here. Elimination. And this reaction is substitution. It means the substitution and elimination, they go side by side. Both the products are possible. That depends upon your reactant. That the reactant is more bulky. Like this reactant is very bulky that this nucleophile cannot easily attack over here. Then it's preferred to lose proton and the eliminated product. Otherwise, if this is not a bulky carbocation, then nucleophile can easily attack, then it will give you the substituted product. Both go side by side. Both the products are formed in different ratio depending upon the reactant. Okay. So, the second type of rearrangement in carbocation is hydride shift there. In hydride shift, H negative shift instead of methyl. Suppose we have Now suppose this is your reactant now, and we are adding this nucleophile, and it undergoes SN2. The first step is to produce carbocation. Carbocation formed is CH3, C, CH3, H. This is now 1 degree carbocation. It undergoes rearrange. Now we have this H negative shift. That's called hydride shift. To produce, again you can see this is 3 degree carbocation. Is more stable. Then this nucleophile attacks over here to give this final product. So this is hydride shift in SN1 mechanism. So this is about the rearrangement. Next come to the second type of reactions that alkyl halides generally undergo. They are elimination reactions. And in elimination, the important reaction is dehydrohalogenation of alkyl halide. Dehydrohalogenation means removal of hydrogen and halogen. Removal hydrogen halogen. Removal of hydrogen and halogen. That's X. Next, suppose we have this type of alkyl halide. Here is a hydrogen. Okay. And here is your halogen. Some base come and take this hydrogen. This pair of electron shift here, and this pair of electron go along with us. This is called beta elimination. As you can see, this carbon is alpha, this carbon is beta. So product formed is ethane. Okay. So this reaction is called dehydrohalogenation. It takes place generally in the presence of KOH, like suppose we have CH3, CH2, suppose we have Br. If we add KOH, alcoholic, but one more reaction of this is, if you add KOH aqueous, both are different. Keep in mind, these two are different reagents, they give different product. When we have a KOH aqueous, it means this KOH aqueous produce nucleophile, and this will be a nucleophilic substitution reaction. It easily replaces this Br. But when there is an alcohol, this acts as a base. Okay, and this acts as a nucleophile. That's the difference. So what different products are formed? In first case, here we get simple nucleophilic substitution reaction, alcohol. But here we get a CH2 double bond CH2, dehydrohalogenation. And this base abstract, this is alpha, this is beta. Abstract protons, suppose there are two protons, I will write it like this and like this. Okay. So now what this base will do, This base take out this hydrogen, bond shift here, Br out. To get ethene plus water plus KBr. So this reaction is elimination. This reaction is substitution. That is the major difference between these two. Just writing alcoholic or aqueous, that makes large difference in the product. Okay. Now, elimination reaction. If we have a simple alkene like this, then there is only one beta carbon. The elimination is easy. Suppose I am taking some more complex reactant. Suppose the reactant is secondary butyl bromide. Adding KOH alcoholic. Now this carbon is alpha. This is beta, this is also beta. You get two products, either you remove the hydrogen from this side or you remove hydrogen from this side. So you will get two products. First is, suppose you are removing hydrogen from this side. This is but1ene. Second is, suppose the hydrogen is removed from this side. You get but2ene. But1ene and but2ene. But2ene is a major product. This is minor because but2ene is more stable than but1ene. That you can use the Senjef rule here. Senjef rule. More substituted alkene are more stable. Just compare but1ene. But1ene is like this, that we have a carbon hydrogen here. This. You can also compare the stability by hyperconjugation structure. but2ene is like this. So this is more substituted, more stable. Whether you talk about the hyperconjugation structures, this is alpha carbon and there are two hyperconjugation structures, and this is alpha and this is alpha, there are 6 hyperconjugation structures. Then only again the but2ene is the more stable. In the mechanism of elimination reaction, like E1, again carbocation is formed as intermediate. So how to distinguish E1 and E2? Let's see. Elimination reactions are also of two types, just like SN1 and SN2 here. If we have E1, that takes place in 2 steps. First step is, suppose we have this alkyl halide. Here when you add KOH or base to it, first step it is you can say that halogen gets removed. That is a slow process. Even unimolecular, that this bond will break. This is a slow step. Carbocation is formed as intermediate. Okay, so this carbon is beta C. Just like SN1, carbocation is formed as intermediate. In the next step, what happens is there is minus H. So this hydrogen gets moved. This bond shift here, changing it to alkene. This is E1. What about E2? Take place in one step. Say, write the same. Bromoethane. Now suppose you have a base, it will take hydrogen from beta. This bond shift here, this will go out. All take place in single step. And you get T. So this is a different mechanism of E1 and E2. And again we know that in E1 the carbocation is formed. So when the carbocation is formed, then you can say that the rearrangement is again possible. Okay. So rearrangement is also possible. For example, if I write so keep in mind which alkene is formed as a major product, you can write it like this. Suppose this is your alkene. Oh sorry, alkyl. Or to take the alkyl halide. This. Adding KOH will produce alkene. So first of all, when this bond is removed, you get this carbocation. This is 3 degree carbocation already. Now hydrogen कहाँ से remove करेंगे? These are the hydrogen beta. These are the hydrogen beta. These are the hydrogen beta. So you have to remove one hydrogen to get the final product. So either you remove from this or this, both are the same thing. So when you remove A, the product formed is like this. So these are the suppose B. So when you remove B, you will get either this side double bond or that side, doesn't matter. So out of these two alkenes, this is more stable. That will be the major product. So this is about the ease of formation of alkene. More substituted alkene is easily formed. That you can compare with the help of that Sanger fluid, as we already discussed. So जितना ज़्यादा alkene stable होगा उतनी ही उसकी formation easily होगी. So more easily means this is highly substituted Cr2. So this will form fast. Second is the most important, the ease of dehydrogenation. Ease of dehydrogenation of alkyl halide follow this order. Like your tertiary butyl bromide, secondary butyl bromide, simply ethyl bromide. So more means 3 degree carbo alkyl halide, that will give you the 3 degree carbocation. 2 degree alkyl halide will give you 2 degree carbocation, and 1 degree will give you 1 degree. So it depends upon the carbocations. This is the ease of formation of alkene and ease of dehydrogenation. Now we will compare simple comparison of these substitution versus elimination. So both substitution and elimination, they go side by side. Product formation, that basically depends upon the 3 factors: nature of alkyl halide, number 1. Number 2, strength and size of these nucleophile. Size of base or nucleophile. Third is reaction conditions. For example, if we start with 2 bromoethane, and we are doing 2 reactions. If your reagent is bulky, like if we are taking CH3 3CO negative, tertiary butoxide ion, and in second case you will take just 2H negative ion. Now this is bulky, so act as a base. This is smaller in size, so act as a nucleophile. So when it acts as a base, it will take out hydrogen from the beta carbon. So what products are formed? In first case you will get CH2, in second case you will get. So it depends upon the size of the reagent which you are using. Like second reaction is you can say is a substitution, and first reaction is your elimination. So nature of reagent also, nature of ArX also affect. If it is 1 degree, generally undergo substitution. If it is 3 degree, it undergo elimination. If it is 2 degrees, like in this case, that further effect depends upon the strength and the size of the nucleophile or base. If the nucleophile is bulky, the reagent is bulky, it will act as a base because it's difficult to tag on this carbon back from back side of Br. So it's easy for this molecule to take out H from here or here. If your nucleophile reagent is small like this OH, it can easily approach this carbon and give rise to substitution product.